Welcome to Somero Matson Group's Axiom ASTM 1155 training course. We created this course for anyone in general who is interested in measuring floor flatness and floor levelness to the specifications within ASTM 1155. We have endeavored to keep all the concepts as simplistic and as visual as possible. It must be said that there are parts of this course where we provide our opinions on topics within ASTM 1155, such as what we think a good final report should look like and why we think you should use perpendicular and parallel line layouts. We also advise that you purchase a copy of ASTM 1155 and read the specification for yourself in addition to going through this course. Lastly, to set your expectations. What you will not learn how to do in this course is how to operate an Axiom 1155. Provided with your purchase or rental of the Axiom 1155 is a complete and comprehensive video series designed to walk you through step by step on how to use the Axiom 1155. Now let's begin. ASTM 1155 is a test method which is used to measure random traffic floors. The result of the tests are reported in F numbers, FF and FL, floor flatness and floor levelness. It outlines the specifics on how to measure a floor, and with that measurement data, do a statistical analysis to infer with a certain level of confidence just how flat and level the entire floor is. There are two types of floors: defined traffic floors and random traffic floors. Defined traffic floors are defined as floors which are designed to have a very specific vehicle traffic pattern across them, and the profiles of these floors are measured along those traffic patterns, and they are measured via different methods such as Fmin. The measurement of defined traffic floors is not currently covered in ASTM 1155, but it is important that you do know the difference. Most of the floors placed in the US are random traffic floors. This means that they are designed to accommodate, probably as you might guess, random patterns of vehicle or foot traffic across them. As a side note, this is not to say that defined traffic floors are not flat or level in areas where the vehicles are not traveling. It's common on those same projects to see FF and FL specified in areas where there isn't defined traffic. Due to this random nature of traffic, I think you may be starting to understand why ASTM 1155 is a statistical analysis. With current methods, you cannot measure a random traffic floor in every possible direction of travel that one may take across the floor. So, ASTM 1155 enables you to use a statistically significant sample set of measurements which effectively allow you to predict, with a certain level of confidence, what the whole floor will look like. In a way, it's like saying that since we know that 75 out of 100 people polled in North Carolina like to drink coffee, we can go on to predict that 75% of the overall population in North Carolina drinks coffee with some level of confidence. As previously mentioned, ASTM 1155 test results are reported in what are called F numbers, FF and FL. Floor flatness, or FF, represents how bumpy the floor surface is, while floor levelness, FL, represents how level the floor is. The higher the reported FF and FL numbers, the more flat and level the overall floor is predicted to be. These images also show you that you can have a bumpy floor that is level, or a flat floor that is not level. These two properties are somewhat independent of each other, and you will learn more about that when we get into Q and Z values in the next few slides. Before we talk about Q and Z values, we should spend a little time talking about the devices used to take the measurements. As you can see, there are two categories of devices, and they both have the same definition: as an apparatus capable of measuring the elevations of a series of points spaced at 12 inches along a straight line on the floor surface. Although both categories have the same definition, the subtle difference comes down to the fact that for a run of a minimum length, the measurements taken with a Type 1 device need to contain 12 sequential point elevation measurements, whereas with a Type 2 device, you need to take 11 sequential measurements. The reason as to why it looks like you're taking 1 point less measurement with a Type 2 device is because technically you're already referencing the back of the device as point number 1. Don't worry too much about remembering this. This will become more clear as we go. What is important for you to know is that ASTM 1155 does in fact allow for different apparatuses to be used to gather the data for the calculation of FF and FL. The most common apparatus for collecting this data is a Type 2 device, and the Axiom 1155 is a Type 2 device because it uses an inclinometer. And without getting overly technical, inclinometers can be very precise instruments which are designed to measure the amount of incline or decline there is in a horizontal surface. In the case of the Axiom 1155, for each measurement you take, it will reference the last point taken and then record and report the change in elevation or amount of change in slope from its last reading. To give you an idea of just how accurate an inclinometer can be, the specialized inclinometers used in the Axiom 1155 have a system accuracy of plus or minus 0.0015 inches. To put this in perspective, a dollar bill is 0.0043 inches thick, which means the Axiom 1155 can repeatedly measure to a precision of less than half the thickness of a dollar bill. Lastly, in terms of precision, ASTM 1155 makes it very clear. The results obtained with this test method will also vary with the precision and bias of the particular elevation measurement apparatus employed. Instrument inaccuracies will always result in a lowering of the reported F numbers. So said another way, the less precise the measurement device you use to gather the data, the lower the results you will get for FF and FL. We're about to explain in detail what Q and Z values are. Our intent of doing so is to give you some understanding of the inner workings of how FF and FL are ultimately calculated. But more importantly, we want to do it to help set the stage for what N-min is. Don't get overly caught up with actually wrapping your head around the specifics of Q's and Z's. Really what we feel is important for the average person to understand is what N-min is and how to calculate it. That way you know how to use it to determine the amount of runs you need to measure. So far we've identified the types of devices used to measure FF and FL. So let's get into the basics on how the actual measurements or data is gathered, and we'll do so as if the Axiom 1155, which is the Type 2 device, is the apparatus being used. Before I show you the rest of this animation, here is something we briefly touched on in a previous slide regarding the difference in a Type 2 device. Remember the subtle difference between a Type 1 and a Type 2 device is that you need 12 subsequent readings for a Type 1 device, but 11 for a Type 2 device. Well, that is because the back of the foot of the device represents the first actual point, and once you gather 11 points, you have technically gathered 12 points. Now let's get back to what I wanted to show you with this animation. FF is calculated using what are called Q values, and Q values are calculated by comparing the amount of slope change, or curvature, between subsequently measured points. Let's go on to the next slide so we can dig into this deeper. As previously mentioned, Type 2 devices use inclinometers, which are designed to measure incline and decline. From the starting point of 0, let's do a quick simulation of taking a few measurement points. You can see here that the inclinometer tells us the first point is negative 1.2 inches below the 0 point. This probably goes without saying, but we are just using simple numbers to prove a point. In practice, you are actually dealing with thousandths of an inch change in 12 inches. Now let's take a second and third measurement. This second point is 2.3 inches above the last point we took, and the third measured point is 2.3 inches above the previous point. Keep in mind, these numbers are not true elevations. At this point, they are just the amount of change from one reading to the next. Now let's tie this back into what Q values are. Qs are designed to help us determine FF, which ultimately represents the bumpiness of the floor. In simple terms, to find the curve of the floor within 24 inches, take the current measurement and subtract the previous measurement. Your first Q, or Q1, would be 3.5 inches, since 2.3 minus negative 1.2 is 3.5. Now, you need to remember back in school when you minus a negative number and it actually turns it positive. That's what's happening here. So we're actually adding 1.2 to 2.3. So in this case, you are actually adding the difference to arrive at the first Q value, again, which is 3.5. A positive Q represents a valley, while a negative Q represents a peak. And the value it has represents how deep that valley or how tall that peak is. No change in Q is totally flat. Q1 is positive, so you have a trough or a valley. Q2 is 2.3 minus 2.3, which is equal to 0 inches. This is actually telling us that there was no change to the actual flatness of the floor between these points. Although these points are not level, it's still flat between these points. And with that, you now have two Q values, which are then used in the overall statistical formula for calculating FF. Hopefully at this point you understand the general concept of Q values. So let's move on and introduce Z values. Now if Q values are used in the calculation of FF, then you may be able to guess that Z values are used in the calculation of FL. Let's collect some points again. Again, these readings are 12 inches apart, and the Q's represent the curvature between 2 points, which end up being 24 inches apart. Each of the values that are being displayed are like before in that they are differences from one reading to the next. Z's represent the difference in elevation of points, which are 10 feet apart. Notice I said elevations. Let's use the slope change values which were used to get the Q values to calculate the actual elevations as they relate back to 0. Now we have the elevational values for each measured point. So if the first measurement goes down 0.1 and the next one after that goes down another 0.1, the elevation of the third point on the line has an elevation of negative 0.2 inches below 0. Does that make sense? Okay, let's keep going. The first point has an elevation of 0. Counting 10 points from that, you see an elevational value of negative 0.1. So to calculate the Z values, just subtract 0 from negative 0.1. So Z1 equals negative 0.1. Let's get our second Z value. Remember what we talked about in the Q's. When you subtract a negative number, it makes it positive. So Z2 is 0.2. A positive Z value means an uphill change from the first value to the 10th value, whereas a negative value will indicate a downhill change from the first to the 10th value. We didn't spend an overly long amount of time talking about Q's and Z's. Again, we want you to just understand them conceptually. On this slide, let's take a bunch of measurements. Don't worry too much about the values of each measurement at this time. What we really want you to understand with this animation is that when you collect measurements along any given line or run, you are simultaneously collecting both Q and Z values. Now if you notice, you actually have 9 less Z values than the total amount of points along this run. This becomes important for the next slide, so remember this. At this point, you might be thinking, okay, I get the whole thing about Q and Z values, but really where's it going? I know I don't just randomly start measuring a floor, taking readings in every which direction in the hopes that I get enough statistical data. No, and you're right in thinking that. There are very specific rules in ASTM 1155 which help you determine the minimum amount of measurements you need to collect. Once you have that number, you can then use it to determine your run layout. We're going to get into your run layouts later, but first let's talk about a minimum amount of data that you need. ASTM 1155 allows you the freedom to take as much data as you want. However, there is a minimum amount of data, and that's defined by N-min. And since you understand in part what Q and Z values are, you should now be able to understand N-min. This is a little bit like the coffee example that we had used earlier. We have to look at a certain set of the population in order to be considered statistically significant. I cannot just ask one person if he or she drinks coffee and then apply that across the entire population of North Carolina. As I mentioned, every section that you measure has a minimum amount of data that you need to collect in order to be considered a good statistical representation of the overall floor. You could say it this way. You need to collect a minimum amount of Z values in a given section of the floor. Since remember, you're also collecting Q's when you collect Z's, and you're actually killing two birds with one stone by saying you just need to collect a minimum amount of Z values. Or you could say it the way ASTM 1155 says it, and just say that you need to collect N-min readings. N-min is just the minimum number of z-values you need to collect. There are two different equations for N-min that you need to use, and they are dictated by the section size. We haven't really talked about section sizes and surfaces, and again, we'll get into that more later as we go. But a section is the area that you're going to test. And if the area of the section you're going to measure is 1,600 square feet or larger, then you will use this equation to determine the minimum amount of z-values that you need to collect. N-min is equal to the area divided by 30. So in simple terms, let's say I have a floor section that measures 3,600 square feet. Then to get the N-min, otherwise known as the minimum amount of z-values that I need to collect for that section size, just take 3,600 and divide it by 30 and you get 120. So you actually need 120 z-values for that section in order to have enough data to be considered statistically significant. This is a good time to get you to recollect what we talked about at the end of the last slide. For every run you take, it ends up that you will collect 9 less z-values than the total amount of points. So if you have a run that's 50 feet long as part of this 3,600 square foot floor section, you're actually collecting 41 z-values for that particular run. And you will need to collect another 79 z-values over the course of the other runs within that section. 120 minus 41 is 79. So in order for you to reach your N-min, you need another 79 z-values. We will go into this more when we talk about surface sections and runs. For instances where you have a floor section which measures less than 1,600 square feet, you will use a different equation for calculating N-min. In this case, N-min equals 2 times the square root of the area. So if you remember back to your school days, when you ask for the square root of a number, you are asking for what number times itself equals the number in question. For example, if I ask you for the square root of 49, you should tell me that it's 7, since 7 times itself is 49. Getting back to the slide, let's say you have a 784 square foot floor section that you want to measure. How many N-mins do you need? Well, N-min in this case is equal to 2 times the square root of 784. First, find the square root of 784, which is 28. Now multiply 2 times 28, and your N-min for this section is 56. Lastly, I should tell you that N-min usually doesn't always come out to be a whole number. I used whole numbers to simplify things for these examples. Here's a bit of a plug for the ASTM 1155 layout app. The app automatically calculates N-min for you, and in situations where N-min has a decimal, it'll automatically round it up for you. Now, if you're not using the ASTM layout app to calculate N-min, whenever there's a decimal, just round up to a whole number. Again, this is the minimum amount of z-values, so rounding this number up will be required. Do not round down, otherwise you will collect less than the specified minimum. On the other side of things, ASTM 1155 puts no upper limit on how much data you need to collect. So be careful to not put yourself in a situation where you're spending tremendous amounts of time measuring a floor and gathering exorbitant amounts of data. In reality, like we said, the amount of data you can gather on a floor is basically infinite. Now let's go over what surface, sections, and runs are. A surface is the entire floor on one level of a building with a specified set of tolerances. As an example, the entire ground floor of a warehouse is 300,000 square feet, and it has an overall specified FF of 50 and an FL of 30. If you had another part of the building on the same floor which has a higher or lower specified FF and FL number, and you would consider it an entirely separate surface. A section is a subdivision of the surface. So for a surface this size, there will be multiple sections. Now let's go over some of the rules for creating a section. A test section cannot measure less than 320 square feet or have a side with less than 8 feet. A test section cannot overlap other test sections. And a test section shall not cross a construction joint. And in case you don't know what a construction joint is, here's the definition as defined by the Engineering Dictionary. The contact between the placed concrete and concrete surfaces against or upon which concrete is to be placed and to which new concrete is to adhere, that has become so rigid that the new concrete cannot be incorporated integrally by vibration with the previously placed concrete. Now, this isn't a rule. This is a general industry standard recommendation that you should create your test sections to be between 2,000 and 8,000 square feet. Again, this is not a rule. This is just a recommendation. This recommendation was created so that you can potentially reduce the impact that a localized anomaly has on the overall numbers. Let's talk a bit more about what you do know to reinforce things a bit. So you know that for one project there may be a couple of different surfaces. You'll be reporting the results of those surfaces as their own individual reports. You also know that each surface may have many sections within it. In keeping with the rules from the last slide, you can technically make those sections as large as you want. However, again, 2,000 to 8,000 square foot sections are the typical norm. You may have a 10,000 square foot floor where you decide to measure it as one test section or break it up into two regular test sections. It's your call. You also know how to calculate the minimum number of z-values you need to collect for each of those test sections. Because, of course, now you know how to calculate n-min. Let's say it's the day's concrete pour or placement of 10,000 square feet, and you're just going to test it as one section. Since the area is greater than 1,600 square feet, you're going to use the equation for n-min, which equals area divided by 30. 10,000 square feet divided by 30 is equal to 333.33. Round that up and your n-min is 334. If you want to collect 335, 338, 345 z-values, it's really your call. The big thing is you need to at least collect the minimum amount of z-values. Now let's make this real world and throw some column boxes and pipes in here. We'll make it even more real world and put some saw cuts in here as well. Now the stage is set and we can start going over run rules. A run is a straight measurement line which cannot measure less than 11 feet in length. Shall not fall within 2 feet of any slab boundary, construction joint, isolation joint, blockout, penetration, or similar discontinuity. This rule has been effectively called the 2-foot boundary rule, and it's in place to omit as best as possible the areas of the slab that need to be finished by hand. But there's 2 exceptions to this rule. And the first is shrinkage crack control joints formed by either partial depth saw cuts or partial depth inserts shall be ignored. Essentially, this means you can measure right over a saw cut. As a technical note, this is a lot easier to do in practice if you have a Type 2 device with feet like an ASTM 1155, which are large enough to span the saw cut and not sink into it. And the second exception to this rule is the area to be excluded using the 2-foot boundary rule does not exceed 25% of the test area. If for some reason it does, then the 2-foot rule no longer applies. Now let's get back to the rest of the run rules. Runs cannot be placed parallel to each other closer than 4 feet. Data gathered from each run shall only be excluded when it can be demonstrated that the test apparatus reported inaccurate values or the test procedure of the test method was not followed. There could be a situation where at the end of a run you notice that there was something stuck to the bottom of one of the foot pads. The best thing to do is to clean off the foot and retake the run, making a note of the issue with the previous run so you have documentation as to why you have omitted that run. At this point, you know the run rules and you know the exceptions to the run rules. The last piece of the puzzle you need to know is how to lay out your test runs. If you're being paid to perform an ASTM 1155 compliant test, then undoubtedly you want to produce the most accurate and repeatable test results that you can. In keeping with this, you will want your runs to be methodically laid out in such a way that you have documented both their direction and their locations. ASTM 1155 gives us 2 options of placing the runs uniformly across the test section, and you can only use one of these methods per test section. Also, as a side note, by uniformly, you are endeavoring to place the runs at equal spacings apart from each other. Granted, there may be situations where you cannot do this and have to shift a line over slightly just to avoid a column or some other protrusion, so you can stay in keeping with the 2-foot rule. The first layout method is 45 degrees to the longest construction joint. Before we go into how to lay out your runs using this method, we recommend that in most cases it's of far more value to all parties involved to use the perpendicular and parallel method of run placement. Not only is it easier to go back and replicate where you placed your runs, but it gives the concrete contractor and the general contractor data that they can use to see what may have gone wrong during the placement process, should a situation arise where they did not meet the specified numbers. So let's get back to the 45-degree run layout method. First, let's create our 2-foot boundary. Now let's lay out our runs using this 45-degree layout pattern. For step 1, you will find the longest test boundary to your section, and you will place your runs 45 degrees to that boundary. Unless the section is an exact square, you cannot do corner-to-corner diagonals. The measurement line should truly be 45 degrees to the longest boundary. Step 2. So long as the runs are configured at 45 degrees to the longest boundary, and you gather the proper amount of z values to have enough to satisfy the amount required by n-min, then you are free to position the runs uniformly and at lengths greater than 11 feet, in keeping with the 2-foot boundary rules. So in this case, we know n-min is 334 for this particular section, and we can place our runs like this. Now our red runs are 90 feet long, and our blue runs are 80 feet long. They are both positioned 45 degrees to the longest boundary. 90 minus 9 is 81, so we get 81 z values for each red run. And then we get 80 minus 9, which is 71 z values for our blue runs. And that adds up to a total of 375 z values for this run layout. This is certainly more than the minimum, and these runs are uniformly placed, so we are good to go. As you can see from this layout pattern, you do not need to have the same number of runs going in the same direction, nor do they have to be the same lengths. As we suggested earlier, doing this run pattern makes it difficult to troubleshoot what may have actually gone wrong during the placement process. Additionally, as you can see, it may be harder to locate and recreate these exact runs. The only time you absolutely have to use this layout pattern is when the width of the section you are measuring is less than 25 foot wide, at which point this is your only run layout option. Now, let's discuss what we were calling the preferred method, the perpendicular and parallel lines layout method. In our opinion, this is the most useful and more easily repeatable method that you should use to lay out your floors. From a forensic standpoint, here's a quick example of why this method could be helpful to your customer. Say you can see a clear trend in low FL numbers going east to west, and higher FL numbers going north to south. Perhaps this is an indication that the laser used during the placement was out of calibration. That is why our ASTM layout app defaults to this method, and it's only when you try to enter in a dimension that's less than 25 feet in width that the app will generate a warning and tell you that you need to use the 45-degree method. That said, here are the run layout rules for this method. Rule number 1. They must be perpendicular and parallel to the longest test section boundary. If the test section is irregular or triangular in layout, then you put your runs in relation to the longest boundary of that triangle. Rule number 2. You need to have the same number of lines in each direction. Rule number 3. The runs must be of equal aggregate length in both directions, and as you can see, there are 2 longer lines and 2 shorter lines. But if you take the aggregate length of the lines, which means you're just adding up the total length in either direction, then it will be the same. Laying out runs with short legs and long legs can be a bit tricky, and generally it's just easiest to use the same length runs as your width minus 4 feet, like we did here. The last thing I need to mention before we go on to the next slide is this. You cannot use both layout methods on the same section. That said, you can use the 2 methods for different sections within the overall surface. Alright, let's go on to the next slide. So there is a fair bit of flexibility on how one may lay out their runs within a section, and we should spend a few moments talking more about a popular scenario you may run into. It's common for a day's placement to include a jog off to one side. From a testing standpoint, you now have a bit of an interesting situation. Do you break the placement into 2 or more test sections like this? Well, technically you could. Since the smaller section is more than 320 square feet, you can even use perpendicular and parallel lines since the width is 25 feet. Remember, it's less than the 25 feet that is the breakpoint that forces you to use the 45-degree method. The only gotcha is that you cannot observe the 2-foot boundary rule in this section. Let's draw in the 2-foot boundary so we can do the math and show you why. Here's the general equation for determining the percent excluded. It's actually pretty easy. You take the total square footage of the section. In this case, it's 25 by 30, which is 750 square feet. Then you get the total square footage of the area within the 2-foot boundary, which is 26 times 21, which is 546. Then you subtract the area from within the 2-foot boundary from the total square footage to get 204. All you do now is divide 204, which is your total excluded area, by your total square feet, and you get 0.272. Now, to turn this into a percentage, you just multiply 100. In this case, it's 27.2%. Do you remember one of the run rules? One of them said that the area to be excluded using the 2-foot boundary rule does not exceed 25% of the test area. Well, in this case, it does. So, the 2-foot boundary rule no longer applies. By the letter of the law, you certainly are within the rules of ASTM 1155 should you decide to make this into its own small section and do perpendicular and parallel lines which run all the way to the form's edge. However, you are unnecessarily creating a situation where a contractor could receive lower numbers for this particular section because you are now forcing yourself to measure up to a form edge, which is now accounting for more area that was probably placed and finished by hand. Let's look at this from another direction. We'll try to do this as just one section, as well as try to avoid using the 45-degree line layout method. Total square footage for this example is 6,750. Now let's draw in our 2-foot boundary and get our square footage so we can calculate and check to see if the excluded area is not more than 25%. So 71 times 76 is 5,396, and 30 times 21 is 630. So the total area within the 2-foot boundary, which is your test area, is 5,396 plus 630, which is equal to 6,026. So we know the total square feet, and we know the square feet within the 2-foot boundary, so now we can just plug this into the equation at the top of the slide. 6,750 minus 6,026 is equal to 724. So your total excluded area is 724 square feet. Now, we just divide the total area by the total square feet and multiply by 100, and we get the percent excluded. 724 divided by 6,750 is equal to 0.107. Now, let's multiply that number by 100 to turn it into a percentage. We get 10.7%, which means we can observe the 2-foot boundary rule. Now, let's calculate our n-min. Remember, that value represents the minimum number of z-values that we need to collect for a section this size. And since the overall area is larger than 1,600 square feet, you can use n-min equals area divided by 30 to calculate your n-min. In the first example, with the small section, you would have to use 2 times the square root of the area to get n-min. That is because the area is less than 1,600 square feet. Now, in this example, 6,750 divided by 30 is 225. You need to collect a minimum of 225 z-values for this section size. So, knowing we need to collect at least 225 z-values, let's lay out our runs. To get the little jog, we will just use 2 21-foot runs, and then once we get out into the larger area, we will use 4 71-foot long runs. So long as we keep our runs of equal aggregate length, we're good. So in this example, there are 2 71-foot long runs going east and west, and 2 going north and south. Then to get some measurements in the jog, we have a 21-foot long run going east to west, and 1 going north to south. As far as getting enough z-values, we have plenty. If you recall, calculating the amount of z-values you get from a given run is very simple. Just subtract 9 from the distance of your run. So, 71 feet minus 9 is equal to 62. Multiply that by 4 runs, and we get 248 z-values. And then 21 minus 9 is equal to 12. Now we're going to multiply that by 2 runs, and that equals to 24 z-values. So your total z's you will collect are 248 plus 24, which equals 272 z's, which is plenty. So again, you have a fair bit of flexibility with your layouts. Let's go on to the next slide to run through the process one more time to reinforce all this stuff. Here's an example of a test section, which is part of an overall surface. Like I said, it's industry standard to create test sections which are 2,000 to 8,000 square feet. In reality, depending upon the amount of floor placed in a day, you may find yourself testing several sections a day. But let's go through the steps for this section. Step 1. Let's find the area. 80 times 100 is 8,000 square feet. Step 2. Let's calculate N-min. Because the square feet is over 1,600 square feet, you will use area divided by 30 as your equation for N-min. 8,000 divided by 30 equals 266.66. Remember, this is the minimum amount of z-values you need to collect. So let's just round up to get 267. Step 3. Let's calculate the amount excluded with a 2-foot boundary. We have to make sure that we can in fact use the 2-foot boundary rule for our run layouts. To get the percent excluded, use this equation. Let's do this one piece at a time. Total section square feet minus square feet of tested area within the 2-foot boundary is equal to the total excluded area. So 8,000 square feet is our total area subtracted by the measured area within the 2-foot boundary equals 1,464. Now let's do the other half of this equation. Then you take the total excluded area divided by the total square feet and then multiply by 100 to get the percent excluded. In this case, 1,464 is your total excluded area divided by your total area, which is 8,000. The answer comes out to 0.183. Let's turn it into a percentage by multiplying 100. And then you get 18.3%, which is certainly less than 25%. So the 2-foot boundary rule is in effect, and your runs need to stay 2 feet away from form edges, pipes, and the rest of the stuff mentioned on a previous slide. Step 4. Determine your layout method. You can choose from the perpendicular and parallel line layout or 45 degrees to the longest boundary lines layout method. Again, we default to the perpendicular and parallel lines. Now we have all the information we need to put our runs on this section. Using the longest boundary, which is 96 feet, we will lay out our lines perpendicular and parallel to that boundary. Step 5. Determine your run lengths and the amount of z-values per run. Really, the simplest thing to do to get your run length in an open area like this is just to make your run lengths equal to your shortest side within the 2-foot boundary. In this case, it's 76 feet. And how many z-values do you get? Well, 76 minus 9 is equal to 67. So at this point, you get 67 z-values per 76-foot long run that you do. So if you do 4 runs, which are 76 feet long in the north, south, east, west directions, you have a total of 268 z-values. Look to the left under step 2, and you will see that the N-min for this section size is 267. So if we do 4 runs, which are 76 feet long, we are collecting just enough z-values. Here's just one way to do that, which meets all the requirements of ASTM 1155, in that we have enough z-values, all the runs are perpendicular and parallel, they're evenly spaced, they're within the 2-foot boundary, and of equal aggregate length in both directions. Prior to going out onto a job site, we strongly recommend that you acquire the plans for the project so you can have your sections and runs laid out ahead of time. Although the math is simple and planning these runs is pretty straightforward, it's made a lot more difficult when trying to figure this out on site with a bunch of people talking to you. Now I hope at this point this stuff is starting to make sense, and while the free Axiom Layout Companion app figures out the minimum run lengths for you based on a square or rectangular section, it's really best for you to know how to do it without the app, just in the event that you have to. From this slide, we have a somewhat more oddly shaped floor, and using this shape, we want to make it painfully obvious that ASTM 1155 allows you some creative license when you create your sections. The overall square footage of this floor is 26,000 square feet. There is nothing in ASTM 1155 that says you cannot treat this entire floor as one section, like this. Or if you are more conventional, then you may opt to lay out your sections like this. Of course, you can do it this way as well, especially if the little sections still allow you to use the 2-foot boundary rule. For the long section, your run layout may look something like this. At this point, other than gathering job-specific information for your report, you now should have a solid understanding of how to break a floor up into sections, calculate the amount of data that you need to gather, which is N-min, as well as lay out your runs. As far as actually taking the measurements with an Axiom 1155, this is covered in the free video series that comes with the purchase of the Axiom 1155. Basically, you just walk the device end for end along the run lines that you've laid out. You need not memorize the following calculations. These are done automatically within the Axiom phone apps and the report generator. This is the formula for FF.
The Q values gathered are simply entered into this formula along with the standard deviation of the Q values here. A similar procedure is followed using the Z values to calculate FL with this formula. For any given run of Q and Z values, there's a corresponding FF and FL value. For calculating the local FF and FL values for a section, one must combine all the runs, and a common mistake is to simply average the FF and FL values for all the runs in a section to derive the local FF and FL values. This is okay only if all the runs are of equal length. The correct method is to take into account the run lengths using this formula. Now to combine the local FF and FLs for each section to determine the overall FF and FL of the entire surface. Again, a common misconception is to simply average each of the section results together. This again is okay only if all the sections are of equal size. The correct method is to take into account the area of each section using this formula. Doing it this way allows for a larger section to have more statistical significance or weight in the overall calculation of FF and FL than a smaller section does. If you'd like to go over this in more detail, it is explained within ASTM 1155. Let's go on to the next slide.
In this final section, we go over what a good final report should include, some of which is specifically required by ASTM 1155, and some of which we feel just needs to be included because it makes for a more complete and professional report.
Aside from the obvious report results for F numbers, your report should also include 1. The name and location of the subject building, 2. The installation date of the floor, as well as the date you're testing it. Now as a side note, per ACI 117-90, that requires the specified concrete floor tolerances be checked within 72 hours after floor installation. This means that you, as the person testing the floor, has 72 hours from the date the particular section was placed to test it. If you can't perform this test within 72 hours, then your test is no longer in compliance with ASTM 1155. 3. The specified overall FF and FL values and the minimum local values if there are any. Note, the minimum local values are the lowest allowable values that any one section in the overall surface can have. 4. The make, the model, and the serial number of the test apparatus. 5. The name of the individual taking the test. 6. Your run names, layout, and direction of runs. Now ASTM 1155 doesn't say that you need to include this in your report, but if you're going to take the time to measure and lay out your runs on the job, why not include this info in your report? Also, in terms of naming your runs, the Axiom 1155 auto-generates a run name for each run in sequential order, i.e. run 1, run 2, run 3, run 4, and so on. This is the cover page for a fake report using the Axiom desktop report generator. On this cover page, you can see it includes much of what we talked about in the last slide. Here is the name and location of the subject building. Here is the installation date and the test date. Here is the specified overall FF and FL, and the minimum local FF and FL numbers. The make, the model, and the serial number of the test device, as well as the person who took the measurements, and who they did them for. Let's look at a couple more pages that are created using the Axiom desktop report generator. By looking through this report, it should help to tie together what you have already learned through this course, and at this point, it should all start to make sense to you. Here's the layout page that comes as part of the Axiom desktop report generator, and you can, and we believe, you should provide a page like this with all of your reports, regardless of whether or not you are using an Axiom 1155. This helps everyone to see where the runs were taken. If there is a run that has low numbers, they can reference this drawing, and in many cases, you can correlate real-world situations with the results in that location. Perhaps there was an issue during the placement, and there was a cold joint along that run. Or there were reflection issues with the laser controlling the screed in that location. The list goes on. But in summary, a sheet that shows you where all your runs are and the direction you took them in is very helpful. Here is the inspection report page on the left side, which gives us further information about the individual run results. You will see run 1 in section 1 is 67 feet long and has a measured FF of 40.331 and an FL of 41.512. Let's get off track here for a moment. You'll also see that the run results in each section are reported with confidence intervals. More specifically for ASTM 1155, the section and run results are reported at a 90% confidence interval. As stated in ASTM 1155, the confidence interval is the confidence in the ability of a certain size sample to estimate the statistics of an entire population. It's expressed in terms of confidence intervals. Said another way, given the amount of data that you've collected, 9 times out of 10, the actual F number of the floor will fall between the upper and lower limits of this test method. I'll continue reading from ASTM 1155. Since it's impossible to be certain of the exact FF flatness or FL levelness numbers of any floor, no matter how many readings are taken, some statistical uncertainty will always exist. Report the results of this test method as a range of possible F numbers at the prescribed 90% confidence interval. Okay, that said, let's go back to the results page. As a concrete or general contractor, how can you use this information? Well, this is the point we've been trying to drive home as the major benefit of using perpendicular and parallel line layouts. If you refer back to the layout image from the previous slide, you now can see where run 1 was taken and the direction it was taken in. In this case, it was west to east. Compound that with the information shown in the graphs for run 1, which, by the way, the Axiom desktop report generator creates automatically as part of your report, you can see the elevational changes over the course of the run. You can also see here that run 1 started to go uphill at the end of the run. If you put 2 and 2 together, this could be telling you that the form edge is set higher on that side. Now remember, we are using the 2-foot run rule, so run 1 starts 2 feet from the west side and stops 2 feet from the east side. Now as a concrete contractor, you know that during a typical floor placement with a laser screed, it's common to screed that part of the floor by hand, in which case people run their screed on the top of the form and the previously struck off concrete from the laser screed. In this situation, you can see that the form, which is incorrectly set at a higher elevation than that of the laser screed, has an effect on the F numbers. So you can use this information to both diagnose and improve your processes. So our parting words for you are that you should endeavor to make sure that everything you've done for and during your testing is laid out properly, documented properly, and done so objectively. And you should plainly and descriptively state your findings. Thank you for your time, and we hope that you have found this course both informative and educational. If you have any further questions, please do not hesitate to call or write us directly.